एवरीवन, मेरा नाम अवनी है। वेलकम बैक टू माय यूट्यूब चैनल। इन दिस सीरीज हम सीख रहे हैं डेटाबेस मैनेजमेंट सिस्टम एंड टुडे वी आर गोइंग टू लर्न अबाउट यूनिट 4 which is relational database design. In this video we will be covering all the following topics which you can see on the screen one by one. So without wasting any more further time, let's get started. So हमारा पहला टॉपिक है functional dependency and its types. So without wasting any more further time, let's get started with our first topic which is functional dependency and its type. अब ये functional dependency होता क्या है, पहले ये समझते हैं। जैसे कि यहाँ पे एक टेबल है, स्टूडेंट टेबल है। Let this table be R as a relation. So let R be relation schema having an attributes A1, A2, A3 and so on. So this is A1, A2, A3, A4. Let's call that. So let attributes X and Y are two subsets of attributes of relation R. Let's say this is my X attribute and these are my Y attribute. So if the values of the X component of a tuple uniquely or functionally we can also say determine the values of the Y component, then there is a functional dependency from X to Y, which means on the basis of X, if I can determine the values of Y, then it is called as functionally dependent. So this value is determinant and this value is dependent. मतलब रोल नंबर मेरा X है, रोल नंबर के बेसिस पे मुझे बाकी सारी वैल्यूज अगर मिल रही है तो ये Y डिपेंडेंट हो जाता है एंड X डिटर्मिनेंट हो जाता है. इट इज डिनोटेड बाय दिस एरो. सो रोल नंबर determines name, SPI and BL. It is referred as Y is functionally dependent on the X or X functionally determines Y. So we can either say this that X determines Y or Y is determined by X. Both the ways एक ही मतलब होता है. Right? Let's see this with the diagrammatic representation also. Let's take an example. Consider the relation account. एक account table है, उसके अंदर account number, balance and branch. ये तीन attributes है. Account number can determine both balance and branch. So इसमें x की value क्या हो गई? Account number becomes my x and balance and branch becomes my y. So there is a functional dependency from account number to balance and branch. This can be denoted as X determines Y. So account number determines balance, comma, branch. Now let's understand the types of functional dependency. Full functional dependency and partial functional dependency. In a relation, the attribute B is fully functionally dependent on A if B is functionally dependent on A but not on any proper subset of A. Example is roll number, semester, department name. ये तीनों मिला के it can tell me the SPI. We need all three attributes to find the SPI. जिसका मतलब है SPI which is B attribute is fully functionally dependent on all three of them. इसमें से कोई एक भी कम होगा तो we cannot get the SPI's value. This is called as full functional dependency. अब partial dependency में क्या होगा? The attribute B is partially dependent. B is functionally dependent on A as well as on any proper subset of A. जिसका मतलब है enrollment number, department name can determine SPI. So this is my B attribute and this is my A. So B is determined by A, but SPI could also be determined by just enrollment number also. So enrollment number is sufficient to find SPI. Department name is not really required to find SPI. So then this is a partial functional dependency. Now let's understand transitive functional dependency. In a relation, if attribute A determines B and B determines C, then we can also say that A can determine C, which means C is transitively depends on A via B. For example, यहाँ पे एक table है, subject faculty. We have given the subject, faculty and the age. So example, subject determines the faculty and faculty determines the age. Then we can also say that directly subject can also determine the age. Therefore, as per the rule of transitive dependency, subject can determine age should hold. That makes sense because if we know the subject name, we can know the faculty's age also. Simple as that. Let's understand two more types of functional dependency. One is trivial functional dependency. Next is non-trivial functional dependency. In trivial, X, which is the determinant, and Y, which is the dependent, is a subset of X, which means Y is also a subset of X. Example is roll number, department name, semester can determine the roll number. Now, roll number is also included in this set of X. So, this is a trivial functional dependency. Now, non-trivial functional dependency exactly uska opposite hai. Y is not subset of X. Roll number, department name, semester determines the student name, but student name we can see it's not there in the set of X. So, that is non-trivial functional dependency. Now, let's understand the next topic, which is Armstrong's axioms or inference rules. These Armstrong axioms or inference rules are also the properties of functional dependency. These are set of rules used to infer or derive all the functional dependency on relational database. अगर हम ये rule follow करेंगे, so it will be very easy to find any kind of a functional dependency. So the first one is reflexivity. If B is a subset of A, then we can say that A determines B. We have seen this in the trivial type of functional dependency already. अगर B A का subset है, then this is valid functional dependency. Let's understand augmentation. If A determines B, then we can also say that AC determines BC. C is the new variable. So, if any new variable joined with this, so we can also say that AC can also determine BC. Self-determination is simple. If A determines A, that is also a valid functional dependency. Next one is transitivity. If A determines B and B determines C, then we can say that A can determine C. We have already seen this in the transitivity type of functional dependency. Now let's understand the pseudo-transitivity. If A can determine B and BD can determine C, so you can already assume then AD can also determine C. Like this rule also says, it's just that new variable has been added over here. Decomposition. If A determines BC, so we can decompose. A can determine B also and A can determine C also. Union. If A determines B and A determines C, so together A can determine BC both. This is the union rule. Composition. If A determines B and C determines D, then AC determines BD. AC can determine BD. So this was the rule of composition. Here we composed it, here we decomposed it. All this inference rules, we will be using it further. Let's understand our next topic, which is closure of a set of functional dependency. अब closure क्या होता है? अगर आपके पास given a set F है, functional dependency, there are certain other functional dependencies also that are logically implied. ये logically implied कैसे होगा? By the rules जो हमने अभी सीखे हैं. Example, F is a relation in which A determines B and B determines C, then we can infer that A determines C. ये हमने already समझ लिया है with the transitivity rule. The set of functional dependency that is logically implied by F is called the closure of F. जो logically imply हो रहा है from the functional dependency जो आपको दी गई है उसमें से, उसको हम कहेंगे closure. उसको हम denote करते हैं with F plus से. So let's understand this more with an example. Suppose we are given a relation schema. R is the relation in which we have attributes A, B, C, G, H, I, and a set of functional dependencies are A determines B, A determines C, CG determine H, CG determine I, B determine H. So logically अगर आपको यहाँ पे कुछ pattern नजर आ रहा है, कोई rules नजर आ रहे हैं, that A can determine B and you can see B can determine H. So here we can use the transitivity rule. A determines B, B determines H. So we can also say that A determines H. Transitivity rule. So the functional dependency A से हम H की value निकाल सकते हैं, is logically implied over here. Let's see the next one. Next schema. A, B, C, G, H, I, these are the attributes. Functional dependency समझ लेते हैं. A determines B, A determines C. C, G determines H, C, G determines I, B determines H. It's the same example which we have seen in the last one. So this is the first pattern which logically got employed. So this was the first closure. Let's see the next one. Same example है यहाँ पे. एक और चीज अगर आपको यहाँ पे नजर आ रही हो, CG can determine H, CG can also determine I. तो यहाँ पे आपको यूनियन रूल नजर आ रहा है. We have CG which can determine H, CG which can determine I. So we can union that CG can determine HI together. एक और क्लोजर निकालते हैं हम इसमें से. अगर आपको यहाँ पे दिख रहा है A can determine the value of C and CG can determine the value of I. Which rule can be applied over here? We can apply the pseudo transitivity rule. Over here A can determine C and CG can determine I, so we can also say that AG can together determine I's value. So this is my pseudo transitivity rule. Let's see the next one. We have A determines C, so with the augmentation rule we can say AG can determine CG. This is also logically implied. Now AG can determine CG since we have that, and CG can determine I. We have that over here. So over here we can apply the transitivity rule that AG can determine I's value also. So that's the transitivity rule. We can apply multiple rules together to find the final closure. So we actually found out several closures in this. So we can say that F plus equals A determines H, we found out. CG can determine HI, we found that multiple times. AG can determine I. So we found these closures. So इसको आप इस तरह से closure as an answer लिख सकते हो. Let's compute the closure of the following set of the functional dependency A, B, C, D, E, F. A can determine B's value, A can determine C's value, CD can determine E's value, CD can determine F's value, B can determine E's value. So let's find out the closure. A can determine B and A can determine C. We can use a union rule over here that A can determine B, C both over here. CD can determine E and CD can determine F. Again a union rule over here. CD can determine both E and F together. A can determine B and B can determine E. Simple transitivity rule we can use over here. So A can determine C also. A can determine C and CD can determine E. Pseudo transitivity. AD can determine E's value. AD can determine together E's value also. Again over here A can determine C and CD can determine F. Pseudo transitivity rule can determine F's value also. So the final closure which we get is all these values over here. Let's see the next example. AB can determine C, D can determine AC and D can determine E. So over here we can use a decomposition rule. D can determine AC. So decompose, D can determine A also and D can determine C also. That's a decomposition rule. And since D can determine AC and D can determine E, D can determine AC and D can determine E, we can do union. D can determine A, C, E, all three. So this is the closure which we get. So I hope now you are able to understand closure set more further. मैं कुछ questions definitely दूंगी towards the end, so you can try and solve that also. And if you have any questions or queries, आप नीचे comment में mention करके ज़रूर बता सकते हैं मुझे. Let's understand the next closure, which is the closure of attribute sets. Given a set of attributes A, the closure of A under F is the set of attributes that are functionally determined by A under F. It is denoted by A plus. इसे find करने का एक algorithm होता है. The algorithm to compute A plus the closure of A under F we need to find out. So these are the certain steps we will do. Let's understand this more further with an example. So ये algorithm भी आपको better समझ में आएगा. So consider the relation R, which is a schema. A, B, C, G, H, I, these are the attributes. For this relation, a set of functional dependencies F can be given as A can determine B, A can determine C, CG can determine H, and CG can determine I, B can determine H. These are the functional dependencies which are given. We need to find out the closure of AG. So let's see the steps now in the algorithm. Result equals A. While changes to result, we can keep on doing changes to the result and we will run a loop over here for each B which determines Y in the relation F, then we will go in the next. If B is the subset of the result, then we will do the result union with Y. Else the result will be equals result and end. एग्जाम्पल की तरह समझते तो थोड़ा बेटर समझ में आएगा. रिजल्ट हमारा क्या है यहाँ पे AG है जिसका एट्रीब्यूट क्लोजर हमें फाइंड आउट करना है. सो द फर्स्ट कंडीशन है A can be determined B. So A is a subset of AG. We know that. So we can say that result ABG because हमें यहाँ पे उसका union करना है. So we are checking the first condition that A is determining B and A is the subset of AG, then we can do the union of them. यहाँ पे मैंने सारी ही functional dependencies लिख दी है. A determines C, so in this A is also the subset of ABG, so we will now do the union of them. It becomes ABCG. Third one, CG can determine H. CG can determine H. Now CG, is it a subset of ABCG? Yes, it is a subset of that. So result will include CG also in it. Next one, CG determines I. Is CG the subset of ABCG? Yes, it is. So I will also get included in this. B determines H. Is the B subset of ABCGHI? Yes, it is. So again, now I will also new member get added. So the final result, the closure attribute set of AG plus will be ABCGHI. Let's see the next one. Given a functional dependencies FDs for a relation schema ABCDE, F is the functional dependencies which has these set of functional dependency. A can determine BC's value, CD can determine E's value, B can determine D's value and E can determine A's value. So we need to find a closure for A, for CD, for B, for BC and for E. So now you need to solve this exercise by yourself and then check your answers with these answers too. First, to understand what is canonical cover, let's understand what is extraneous attributes. To understand that, let us consider there's a relation R with a schema R equals A, B, C. These are the attributes. And there are functional dependencies. AB can determine C and A can determine C over here. So in AB can determine C, so then B is the extraneous attribute. Now why B is the extraneous attribute? But because if you can see, AB can determine C and A alone also can also determine C. So B की तो हमें ज़रूरत ही नहीं है फिर. The reason is there is another functional dependency that A can determine C, which means when A alone can determine C, the use of B seems to be unnecessary, an extra attribute. An attribute of functional dependency is said to be extraneous if we can remove it without changing the closure of the set of functional dependency. हम ये attribute तभी निकाल सकते हैं जब इसको closure को कोई effect नहीं हो रहा है. AB can determine C and A alone can also determine C. We anyways want to determine C. So why to use an extra attribute which has no use? Such attributes are called as extraneous attributes. Now let's understand what is canonical cover. A canonical cover of F is a minimal set of functional dependency which is equivalent to F, okay, having no redundant dependency or redundant part of dependencies. इसका मतलब है कि ऐसी functional dependencies जो basically minimal set है, जितना उसको minimize हम कर सके उतना करेंगे without repeating lot of redundant या duplicate dependencies. It is denoted by FC. A canonical cover for F is a set of dependencies FC such that ये 4 conditions satisfy होनी चाहिए that F logically implies all dependencies in FC. FC logically implies all dependencies in F. तो जो उसका actual meaning है, जो closure है, वो change नहीं होना चाहिए. No functional dependency in FC contains an extraneous attribute and each left side of the functional dependency in FC is unique, which means there should be no extraneous attribute and each of the left side of functional dependency has to be unique. Understand this with an example. Imagine there is a functional dependency where A can determine B and A can determine C. So we can apply a union rule and make it even shorter and minimal version that A can determine B, C both. So the algorithm to find the canonical cover is this that we need to repeat and use a union rule to replace any dependencies in functional dependency where A1 can determine B1 and A1 can determine B2. So we will use a union rule to combine them that A1 can also determine B1 and B2. Find a functional dependency where A can determine B with an extraneous attribute either in A or in B. So a note would be that test for extraneous attributes done using FC and not F star. This means over here we need to test and check without the extraneous attribute does the meaning change or not. The closure meaning has to be same until F does not change. Let's take an example and say more over here that consider the relation schema where R is the relation and A, B, C are the attributes where the functional dependency would be A can determine BC, B can determine C, A can determine B and AB can determine C. So we need to find a canonical cover and make it a minimal version of it. So let's see, we can combine A can determine BC and A can determine B over here into A can determine BC because this is again a redundant value. We have already the meaning same over here. Next one, a set is A can determine BC, B can determine C and AB can determine C. Now this is the minimal version we have now. Now A is an extraneous in AB can determine C. AB can determine C. The A seems to be extraneous. Why? Check if the result of deleting from AB determining C is implied by any other dependencies. If I remove the A, is it implied by any other dependency? Yes. Can you see B can determine C? So yes, in fact, B can determine C is already present. So set is now A can determine BC and B can determine C. Minimal version. We can decrease this more further. C is extraneous in A can determine BC. So let's check if A can determine C is logically implied by A can determine B and any other dependencies. Yes, using the transitivity rule, if A can determine B and B can determine C, so the canonical cover would be A can determine B and B can determine C. This can imply the entire this functional dependencies which was given earlier to us. So it's a reducing form. You can reduce the functional dependencies as much as you can by applying the rules and by removing the extraneous attributes. But the meaning of the closure should not change. Let's see another example over here. The relation R, there are attributes A, B, C, D, E, F and the functional dependencies are like this. A can determine BC, CD can determine E, B can determine D and E can determine A. We need to find the canonical cover. The left side of each FD in F is unique. Can you see? A is unique, CD again is unique, we do not have that repeated, B is unique, E is also unique, we don't have that repeated anywhere. Also, none of the attributes in the left side or right side of any of the functional dependencies is extraneous. Let's check, is there any attribute which is extraneous? A can determine BC. Can we see is BC or any of that attribute is extraneous? I don't think so because that meaning is not implied by any other functional dependency. Similarly over here also, similarly over here also and here also. I don't see any extraneous attributes. You can take a moment, check by yourself also. Therefore, the canonical cover FC is equal to F. So it cannot be reduced any further because all the functional dependencies over here, left side is unique. We don't seem to find any extraneous attribute also. So ऐसे cases भी हो सकते हैं जहाँ पे आपका functional dependency and canonical cover has the same result. Let's understand the next topic which is decomposition. Decomposition rule तो आपको already याद होगा. Let's apply them. So decomposition is the process of breaking down a given relation into two or more relations. अब canonical में क्या हो रहा था? Multiple relations से हम उसको minimal format एक में या दो में हम बना रहे थे. Decomposition में क्या हो रहा है? एक को हम दो या तीन फॉर्मेट में उसको ब्रेक डाउन कर रहे हैं, तो हम इसको मैक्सिमाइज कर रहे हैं, बिल्कुल कैनोनिकल का अपोजिट. Relation R is replaced by two or more relation in such a way that each new relation contains a subset of the attributes of R. Together, they all include all tuples and attributes of R. So, the types of decomposition which we are going to understand today is lossy decomposition and lossless decomposition. Let's see. what is lossy decomposition? A decomposition of a relation R into R1 and R2 is lossy when the join of R1 and R2 does not yield the same relation as in R. Let's consider this as relation R, this as R1 and this as R2. So when we decompose this relation into two of them, the result which comes is this, which is not similar to the relation R. So in this case, we tend to lose some data, so that's why it's called as lossy decomposition. The disadvantage of such kind of decomposition is that some information is lost during retrieval of original relation. So from a practical point of view, decomposition should not be lossy decomposition, वरना उसका कोई मतलब ही नहीं होगा. Right? Let's understand this now with the second one, lossless decomposition. Consider this as the relation R, R1, R2. इस relation R को मैंने R1 and R2 में divide किया. Now if you see the difference in this and in this is a lot. Over here, account number and balance ये मेरा एक table हो गया and balance and bank name दूसरा table हो गया. If we join both of this, the result becomes this, where the account number, balance and bank name gives a more number of tuples over here. However, over here मैंने account number को दोनों table में डाल दिया, balance and bank name दोनों table में डाला. So now when I join them, the result is exactly same. So ये मेरा lossless decomposition हो गया. This is also referred as non-additive, which means non-loss decomposition, and all decompositions must be lossless. We should not be able to lose any data or add any more data. Now let's understand what is anomaly and its different types. So what is an anomaly? These are the problems that can occur in poorly planned or unnormalized database where all the data are stored in one table. There are three types of anomalies that can arise in the database because of redundancy, which are insert, delete and update. Redundancy का मतलब duplicacy होता है. Again I'm repeating, I have said this already, but just to remind you guys that redundancy means duplicacy. We do not want any kind of duplicacy in our database design. So such kind of anomalies happen during insertion, deletion or updation. Let's see how. So first one is insert anomaly. Let's consider this with an example that there is a relation or a table employee department in which we have employee ID, employee name, city, department ID, department name and manager such attributes. In this we have already seen that employee ID is the primary key. So an insert anomaly occurs when a certain attributes cannot be inserted into the database without the presence of the another attribute. For example, there is a new department which has started, which is the IT department, and we want to insert the data of the IT department. However, there is no employee assigned to that department yet. When we try to insert the data of this department, it will not allow as the employee ID is the primary key, so it cannot be null, it cannot be empty. So this kind of problem in a relation where some tuple cannot be inserted is known as insert anomaly. Let's see the delete anomaly. So again, it's the same relation and employee ID is the primary key. A delete anomaly exists when a certain attributes are lost because of the deletion of another attribute. Let's say I want to delete the data of employee J. Now in this case, the data of manager and the department, everything gets deleted. Now consider there is only one employee in some department, IT department, and an employee leaves the organization. So we need to delete the tuple of that employee. But in addition to that, information about the department is also deleted. This kind of a problem in the relation where deletion of some tuples can lead to loss of some other data which is not intended to be removed is known as delete anomaly. Now let's see the update anomaly. We will use the same table. An update anomaly exists when one or more record or instance of duplicated data is updated but not all. So suppose the manager of CE department has changed. This requires that the manager in all the tuples corresponding to that department must be changed to reflect the new status. If we fail to update all the tuples of given department, then two different records of employee working in the same department might show a different manager and it leads to inconsistency in the database. So if you see, I want to update the manager of the CE department where I put Shah and this same is not updated in the other departments, so the such kind of anomaly is called as update anomaly. How do we deal with such insert, delete and update anomaly? So the one way is, if you see, divide this table into two tables. One could be the employee table and one could be the department table, and we could link them. So such type of anomalies in the database design can be solved by using normalization. Now this is another very important and a very good concept in database management system. So let's understand what is normalization and what are the normal forms which it has. So normalization is the process of removing the redundant data, the duplicate data from the tables to improve data integrity, scalability, storage efficiency. Because अगर duplicate data होगा तो storage भी बहुत ज़्यादा require करेगा. Right? Data integrity means what? Completeness and accuracy of that data. Inconsistency नहीं होनी चाहिए उस data में. Scalability मतलब ability of a system to continue to function well in growing amount of work. Storage efficiency, to be able to store and manage data that consume the least amount of space. And what we do in normalization? It is generally a process involves splitting existing table into multiple more than one tables which can be rejoined or linked each time a query is issued. Like we saw in this example over here, how about if I divide this table into two parts, and most of the problems and anomalies will be solved in such cases. Now, how many forms of normalization are there and which we are going to study also is 1NF, which is first normal form, 2NF, second normal form, 3NF, third normal form, BCNF, which means boys called normal form, 4NF, fourth normal form, and the fifth one, FNF, fifth normal form. As we move from 1NF to 5NF, number of tables and complexity will be increasing, but the redundancy will be decreasing. Start with the first normal form, which is 1NF. So the conditions for a table to be in first normal form are that each cells of the table should contain a single value. It cannot have multi-values. A relation R is in the first normal form if and only if it does not contain any composite attribute or multi-valued attributes or their combination. So this is a very important rule, no composite attributes or no multi-valued attributes. A relation R is in first normal form if and only if all underlying domains contain atomic value. This again says the same thing, that each cell will have only single value in it. Let's see this with an example over here. So we have a customer table which has customer ID, name and address. So in customer relation, address is a composite attribute. Can you see that? There is a Jamnagar Road, Rajkot is. So address is a composite attribute which is further divided into sub-attributes like road and city. So customer relation is not in 1NF because we can see there are composite attributes over here. So the problem will be, it is difficult to retrieve the list of customers living in Jamnagar city from customer table. The reason is that address attribute is a composite attribute which contains road name as well as the city name. It is possible that city name word is also there in the road name over here. So in our example, Jamnagar word occurs in both records. In the first record, it is a part of the road name, and in the second one, it is the part of the city. So to overcome that, what we could do is divide this address into two more parts like road and city. So each cell will have an atomic, which means a unique value in it. So the solution, we divided the composite attributes into number of sub-attributes and insert value in proper sub-attribute. Road alag honge, city alag honga. So you have an exercise to do, that you have to convert the below relation into 1NF, first normal form. There is a person ID, full name and city. I think it will be very easy for you. Do solve it and do let me know how was it in the comment section. Let's see another example over here. Student table with a roll number, name and field in subjects, all the subjects over here. So can you see what is not right in this? So in a student relation, field in subjects attributes, it's a multi-valued attribute which can store more than one value. So the above relation is not in 1F. Now we have to make it in 1NF. It is difficult to retrieve the list of student failed in DBMS. If I want to find out that which of the students failed in DBMS, it will be very difficult for me because now over here DBMS यहाँ है, इधर DBMS at the first place है, इधर at the second place है. So the reason is that the field in subject attribute is multi-valued attribute, so it contains more than one value, so it is very difficult for us to retrieve any single atomic value. So how do we solve this? We divide this field in subjects into another table itself only. So student table, what we do is roll number and name we have put over here, except the multi-valued. In the result table, I have given it one more primary key as result ID, and I have added roll number and subject. I have used the primary key of the student table as the foreign key in the result table to link them, and the subjects over here. So the solution is the first table contains all the attributes except the multi-valued attribute. That is correct, with the same primary key. Second table contains the multi-valued attribute and we have placed the primary key in it as the result ID. We have inserted the primary key of the first table as the foreign key in the second table. So now this is my 1NF form. Let's see the second one, 2NF. Now, what are the conditions for a table to be in 2NF? That it has to be, of course, in 1NF, and each table should contain a single primary key. So, a relation R is in second normal form if and only if it is 1NF, of course, that has to be there, and every non-primary key attribute is fully dependent on the primary key. A relation R is in second normal form if and only if it is in 1NF and no any primary key attribute is partially dependent on the primary key. So we are trying to say the similar thing over here, except the primary key, other elements should be dependent on the primary key. Let's see that. So there is a customer table, customer ID, account number, access date, balance, branch name. These are the attributes over here. But can you see there is one attribute which is not totally dependent on the primary key, and we can see over here there are two primary keys. FT1, the function dependency 1, which is customer ID and account number, can determine access date, balance and branch name. What is function dependency 2? Account number itself alone can also determine the balance and branch name. So balance and branch name are partially dependent on the primary key, which is customer ID plus account number. So the customer relation is not in 2NF. How do we solve this problem? So for example, in case of a joint account, multiple or more than one customer have a common accounts. So if an account A01 is operated jointly by two customers, say 01 and 02, like over here, then data values for attributes balance and branch name will be duplicated in two different tuples of customers C01 and C02. Can you see that? It has been duplicated. So, how do we solve this? We use a decomposition rule over here. We decompose the relation in such a way that resultant relations do not have any partial functional dependencies. So, we remove partial dependent attributes from the relation that violates 2NF. I have decomposed into the table 1 and table 2. Now, account number is one primary key over here and customer ID is another primary key over here. Account number, we are using it as a foreign key over here. And we have placed them in a separate relation along with the prime attribute on which they are fully dependent. The primary key of a new relation will be the attribute on which it is fully dependent. Keep the other attributes same as in that table with the same primary key. So on the account number, balance and branch name are fully dependent. Same over here, the access date and the account number is fully dependent on the customer ID. अब समझते हैं 3NF, the third normal form. Of course, the condition over here is it has to be in 2NF, which means by default it will be in 1NF also, and there is no transitive dependency. Transitive dependency, अगर आपको याद आए कि A is dependent on B and B is dependent on C, then indirectly A is also dependent on C. So that should not be there. A relation R is in third normal form if and only if it is in 2NF, and every non-key attribute is non-transitively dependent on the primary key. We can also say that no any non-key attribute is transitively dependent on the primary key. Let's take an example over here. We have a customer table which has account number, balance, branch name and the branch address over here. So the function dependency 1, we can see that account number is determining balance, branch name and branch address. What is the functional dependency 2? That branch name can determine the branch address. So account number can determine the branch address also using the transitivity rule. So branch address is transitive dependent on the primary key account number. So customer relation is not in 3NF. So the problem will be in this relation, branch address will be stored repeatedly for each account of the same branch which occupies more space. So account number 1, branch name is same. However, the branch address over here is repeated again. Branch name is also repeated again. So this creates a redundancy. So how do we solve this? We decompose the relation in such a way that the resultant relations do not have any transitive functional dependency. I have divided into the table 1 and table 2. Table 1 will have only branch name and branch address, branch name as the primary key, and table 2 will have only the details of account number, balance and branch name. So we remove the transitive dependent attributes from the relation that violates the 3NF. We place them in a new relation along with the non-prime attributes due to which transitive dependency was occurring. So the primary key of a new relation will be non-prime attributes due to which transitive dependency has been occurred. So we keep the other attributes same in the table with the same primary key and add prime attributes of other relation into as a foreign key. So the primary key of the table 1, which is the branch name, has been given in this table as the foreign key branch name. So both the tables could be linked and there is no transitive dependency over here. Let's see the next one, BCNF, boys called normal form. Now the conditions for that should be that BCNF is based on the concept of determinant. Who is the determinant? Account number is the determinant and balance and branch are the dependent. So the left side attribute will be a determinant. Condition for BCNF that it has to be in 3NF and every determinant should be a primary key. A relation R is in BCNF if and only if it is in 3NF, and for every functional dependency that X can determine Y, X should be the primary key. This is the major rule and we can say that in many different ways that every prime key attribute is non-transitively dependent on the primary key, or no any prime key attribute is transitively dependent on the primary key. Let's understand this more with an example over here. Student table, we have a roll number, we have a subject and we have a faculty. 3 attributes. So what is my first functional dependency? That roll number and subject both can determine the faculty. What is the functional dependency 2? That faculty can determine the subject. So we can say that the roll number and subject can determine the subject. That is the transitivity rule. So in functional dependency 2, determinant is what? Is the faculty. This, which is not a primary key. So student table is not in BCNF. So the problem will be in this relation, one student can learn more than one subject with different faculties, then record will be stored repeatedly for each student language faculty combination which occupies a more space. Over here if you see DBMS are more number of times, and same way the faculty data is also getting repeated over here. So here one faculty teaches only one subject, but a subject may be taught by more than one faculty. So a student can learn a subject from only one faculty. Let's see how we can solve this. The solution would be we decompose a relation in such a way that resultant relations do not have any transitive functional dependency. So we remove transitive dependent prime attribute from relation that violates BCNF. So we have removed the faculty and put it in a separate table. Place them in a separate new relation along with the non-prime attribute due to which transitive dependency occurred, which was roll number. The primary key of a new relation will be this non-prime attribute due to which transitive dependency occurred. So in this table, the faculty has become our primary key over here, due to which the transitive dependency was occurring, and we keep the other attributes same as in that table with same primary key and add a prime attribute of other relation into as a foreign key. So over here The subject becomes the foreign key. So faculty, which is a primary key of the table 1, is also the foreign key in the table 2, and this was the attributes due to which the transitive dependency was occurring. Let's see now the multi-value dependency. So for a dependency, x can determine y if for a single value x, multiple values of y exist. Multiple values of y is there, then the table may have multi-value dependency. How do we understand that? There's a student table and there's a student roll number 101 who is studying DS, DBMS, DS, DBMS subjects, and so the redundant data has been repeated. So multi-value dependency is denoted by double lines, and multi-value dependency is represented by x dependent on y with the double lines over here because it is a multi-valued. Now let's understand the next one, which is a 4NF, fourth normal form. The conditions for this will be the relation has to be in BCNF and it cannot have multi-value dependencies like we saw in the previous table. There are multi-value dependencies over here. So let's see the student table over here, the same one. 101 roll number, it has a multi-valued subjects and multi-valued faculty. We can divide this and decompose this into two tables, the subject and faculty separately. So the above student table has multi-valued dependency, so the student table is not in 4NF. How we can make it in 4NF? By decomposing it into two separate tables over here. So a table can have both functional dependencies as well as multi-value dependencies together. Roll number can determine the address. Roll number can determine the subject, which is multi-valued. That's why I have put the double arrows. Roll number can determine faculty also. Again, double arrow because it is a multi-valued. Now how do we solve this? For subject, we have used roll number and the subject as a separate table. For the faculty, I have again used the roll number and the faculty attribute, and for the address, roll number and the address attribute. So like this, each table has a separate data and are linked by roll number as a foreign key. Let's understand now 5NF, which is the fifth normal form. The condition would be the first foremost, we already know that it has to be in 4NF. It cannot have lossless decomposition into any number of smaller tables. So which means student result relation is further decomposed into a sub-relation. So the above relation is not in 5NF. This table can be further decomposed into sub-relations. We have already seen that and we can do that. The result ID, roll number, result could be one table. The roll number, name and subject could be another table. So it could be further decomposed. So this is not in 5NF if there are any lossless decompositions. How we can solve this? That we decompose it more further. Let's see how. Student table, roll number and name, the subject table, subject ID and the name of the student, and the result table with the result ID, roll number, subject ID and the result. Now can this table be further decomposed? I don't think so. So that's why now this is in fifth normal form. Let's start with the next topic. Before I move on to the next topic, let's revise all the normal form once and summarize them. एक rule सारे normal forms में apply होगा, that to be in the next normal form, it is important that it is already in the previous normal form. So there was one NF, जिसका first rule would be it cannot have composite or multi-value attributes, which is no. 2NF के लिए it has to be in 1NF and it should have only one primary key. For 3NF, it has to be in 2NF and it cannot have transitive dependency. BCNF, determinant has to be primary key. 4NF, no multi-value dependencies. And 5NF, it cannot have lossless decomposition. So this is in summary the rules which you should remember, that 1NF, no composite and null attributes, 2NF, only one primary key, 3NF, it cannot have transitive dependency. BCNF, the determinant has to be primary key. 4NF, no multi-value dependencies, and 5NF, lossless decomposition should not be there. Now let's start with our next topic, which is how to find a key. Let me just quickly remove this. Okay, now the conditions to find a key. The attribute is a part of a key if it does not occur on any side of functional dependencies. Second one, the attribute is a part of a key if it occurs on the left hand side of the functional dependency but never occurs on the right hand side. The attribute is not a part of a key if it occurs on the right hand side of the functional dependency but never occurs on the left hand side, then it is not a key. The attribute may be a part of a key or not if it occurs on both the side of the functional dependencies. ये conditions हमें कुछ याद रखनी पड़ेंगी. Then we will know how to find a key. Let's understand this with more an example. Let a relation R with attributes A, B, C, D with functional dependencies. C can determine A, B can determine C. We need to find the keys for relation R. So, attribute not occur on any side of FDs. So, this is correct because as D is not occurring on any side of the functional dependency, attribute occurs on only left hand side of the functional dependencies. Yes, we can see B is appearing only on the left hand side of the functional dependency. Attribute occurs only on right hand side of the functional dependencies. Yes, A can occur on right hand side of the functional dependencies. So this condition says it cannot be a key. However, attribute occurs on both sides of functional dependencies, which is C. C is occurring on the left hand side and on the right hand side also. So the core is the two conditions which is correct, which is D and B. So B determines C and C determines A. So using the transitivity rule, B can determine A also. So BD is the key over here. As these two attributes are the correct ones, so these are our keys. Let's understand with the next example. Let a relation R with attributes A, B, C, D, functional dependencies. C determines D, C determines A, and B determines C. We need to find the keys for the relation. So the core is B, because if you can see over here, B can determine C and C can determine A and D both. So therefore B is the key. Next relation, A, B, C, D with the functional dependency B is determining C, D is determining A. We need to find the keys of the relation. The core is BD over here because B can determine C and D can determine A and D can determine A. So BD is the key. Next one, relation R with attributes A, B, C, D, functional dependencies. A can determine B, B, C can determine D, and A can determine C. We need to find the keys. I want you to try this first by yourself and then look at the answer over here. If you can see, the core is going to be A. Q because A can determine B over here and C can determine D. So A is a key. The core is A because A can determine B and C can determine D and A can also determine C. So the core is A. A is our key. Next example देखते हैं. We need to find a candidate key, again a key, and we need to check for the normal forms over here. Suppose we have given a relation R with 4 attributes A, B, C, D. For each of the following set, we have functional dependency B can determine C and D can determine A. We need to identify the candidate key and also the best normal form which it satisfies 1NF, 2NF, 3NF or BCNF. So the candidate key over here we can see B can determine C, D can determine A. So the candidate key will be BD. So relation R is in 1NF but not in 2NF. Why? In above functional dependency there is a partial dependency. How we can understand that? Because B can determine C and C depends only on B. But the key is BD. So the C is partially dependent on key BD also. Same way in the functional dependency D can determine A. A depends only on D. But the key is BD. So A is partially dependent on key BD also. The functional dependency over here is C can determine D, C can determine A and B can determine C. what will be the candidate key over here? The candidate key over here is only B, because as you can see, the left hand side element, the left hand side attribute is again getting repeated, and B is the only one which is not getting repeated over here. We need to identify the best normal form. The relation R is in 2NF but not in 3NF. Why? Because in above functional dependency, there is a transitive dependency. So as per functional dependency, B can determine C and C can determine D. So we can also say that B can determine D. So D is the transitive depends on the key B. As per functional dependency, B can determine C and C can also determine A. So then we can also say that B can determine A, again using the transitive rule. So A is transitive depends on the key B. Let's see the next one. Over here in the functional dependency, A can determine B, BC can determine D, and A can determine C. So the candidate key, very simple over here, is A. Relation R is in 2NF but not in 3NF. Why? Because again there is a transitive dependency over here. As per functional dependency, A can determine B and A can determine C. So we can also say that A can determine BC using the union rule, and as per function dependency, A can determine BC, A can determine BC, and BC can determine D. So then A can determine D also using the transitive rule. Let's see the next example. Functional dependencies, A, B, C can determine D and D can determine A. We need to identify the candidate key. What will be the candidate key? A, B, C and B, C, D. How? Relation R is in 3NF but not in B, C, and F. In the above functional dependency, both function dependencies have the prime attribute which is D and A. D and A in dependent right side. Let's understand how to normalize the database. As a software contract and consultancy firms maintain the details of various projects in which its employees are currently involved. These details comprise of, for example, employee number, employee name, date of birth, department code, department name, project code, project description, project supervisor. So you have to assume the following. Each employee number is unique. Each department has a single department code. Each project has a single code and supervisor. Each employee may work on one or more projects, obviously possible, and employee names need not be necessarily be unique because वो repeat हो सकते हैं. Project code, project description, project supervisor are the repeating fields which will be there. So we need to normalize. So we need to normalize this data into maybe the third normal form. So now let's make this into a table over here. मैंने ये सारे attributes properly एक ही table में डाल दिए हैं. Like it was displayed over here, employee number, employee name, date of birth, department code, department name, project code, project description and supervisor. This is my normal form. मैंने directly एक table में डाल दिया. अब इसको हम convert करते हैं into 1NF. So to do that, I have divided this into the two tables over here. Employee number, employee name, date of birth, department code, department name. ये मेरा एक table हो गया. एंड एम्प्लॉय नंबर से मैं प्रोजेक्ट की डिटेल्स भी निकाल सकती हूँ कि कौन सा एम्प्लॉय कौन से प्रोजेक्ट पे काम कर रहा है विद द प्रोजेक्ट कोड एंड प्रोजेक्ट डिस्क्रिप्शन एंड प्रोजेक्ट सुपरवाइजर. दिस इज माय फर्स्ट नॉर्मल फॉर्म. अब इस फर्स्ट नॉर्मल फॉर्म से 2NF में कैसे कन्वर्ट करेंगे? द एम्प्लॉय टेबल रिमेन्स द सेम, द एम्प्लॉय टेबल रिमेन्स द सेम, बट द प्रोजेक्ट टेबल कैन बी फर्दर डिवाइडेड. Project code, project description, project supervisor becomes my one table, and with the employee number I can determine the project code. So this becomes my second table with project code being the foreign key from the project table. अब इसको further 3NF में कैसे divide करेंगे? Department का अलग table बना देंगे, project का अलग table and employee number का अलग table. Now this cannot be further divided. So this is my last normalized form which is 3NF. ये क्वेश्चन एक बार फिर से देखना and try to solve it by yourself also. All these conditions must be satisfied. Now these are few questions which are usually asked in exams of unit 4. You can try to solve each of them. If you solve all of them by yourself, then you would be able to score very good in this unit. Take a screenshot of this and try to solve this question. If any doubts or queries, you can mention in the comment section also. These are another questions. अगर आपको वीडियो समझ में आया है then do give a like and in the comment section आप ज़रूर लिख के बताना कि आपको समझ आया है, you have understood it, and also do subscribe my channel for the next video. I will see you in unit 5. Thank you very much.